Okay, so we left off on basically we talked about strong acids and strong bases. They completely dissociate. So if I have a 0.1 molar solution of hydrochloric acid, HCl, it's going to completely dissociate into H plus and Cl minus. And so the H plus is going to be 1 molar, 0.1 molar, and the chloride is going to be 0.1 molar. So, and that's the way strong acids and bases work. And we've seen that if it was, for example, like calcium hydroxide, a strong base, both of the hydroxides are actually strong. So if I had a 0.1 molar solution of calcium hydroxide, I'd have 0.1 mole of the calcium ion, but because there's two hydroxides, I'd have to double that for the hydroxide. So I'd have a 0.2 molar solution of hydroxide. So strong acids and bases, we generally write a single arrow, and they completely 100% dissociate. Again, that's not really the full truth behind it, but for now that works. Next, I want to get into our weak electrolytes, our weak acids, and our weak bases. And for that, we're going to have to show them as being in equilibrium, because we're going to find out that our weak acids only partially dissociate. Generally, a small fraction of them actually dissociate to increase the hydrogen ion concentration. Or our bases only react to form a very small amount of our hydroxide ion concentration. So we're going to have to treat these differently. Again, it's just equilibrium. It's just like we did in the last chapter, in chapter 15. It is just, again, a weak equilibrium. We're going to have to use ice tables again. We're going to have to look up the K values, the equilibrium constants, which we're now going to give fancy symbols like Ka and Kb, but they're still just equilibrium constants. Everything that we did in chapter 15 still applies, okay? But we're going to find some tricks so that we don't have to solve the quadratic formula all the time. Then we're going to talk about, at the end of this chapter, we're going to talk about the acid-base properties of salts. So again, here we have an acid, and this would be its conjugate base. Well, it is a base. So that means that that conjugate base is going to react with water to reform the acid, right? So to reform that original acid, but it's also going to increase the hydroxide ion concentration. So we're going to look at how salts can either be acidic, basic, or neutral. And then in the next chapter, we're going to start talking about buffers. And that's basically where buffers basically simply has approximately equal concentrations of acid and its conjugate base. And all a buffer does is try to prevent the hydrogen ion from the concentration from changing that much. And we're going to find out it's very effective, okay? So a buffer, if I just add extra acid or extra base to it, the hydrogen ion concentration is going to remain fairly constant. So that's what a buffer does. And then in the next chapter, we're also going to talk about titration curves, okay? And how we can quantify, how titration is really important, and how we can quantify not only the concentration of an unknown, but we could determine the pH of a solution as it passes through the entire titration curve, okay? Okay, so let's start with weak acids. So the acid ionization constant, again, this is just the equilibrium constant for a weak acid dissociating into H plus or hydronium ion and whatever its conjugate base anion is. So an example of that, of course, is acetic acid. Okay, so here's our acetic acid. We throw it in water. The hydrogen ion transfers a hydrogen to the water to form the hydronium or hydrogen ion, and leaves behind our conjugate base, which is simply the acetate. So this is our conjugate base anion, right? That is the conjugate base anion would be our acetate in this case. Now, because acetic acid is a weak electrolyte, like I said, only a very small portion of it actually ionizes, and I'll show you that here at some point. So again, because this is simply an equilibrium, well, we're going to have an equilibrium constant, and we're going to call it the acid ionization constant. So instead of just K, we're going to call it K subscript A. So this is our acid ionization constant. So if you want to know if something's an acid, You simply look up in the tables of chemical data, and if it has a Ka value, well, that means it's a weak acid. Strong acids won't have a Ka value, right? Because they 100% dissociate, so there is no equilibrium. Now, of course, we know that that's not true. It simply means a strong electrolyte has a Ka value that's probably greater than 1, or at least close to 1. So generically speaking, then, this would be our weak acid. And again, it would transfer its hydrogen to the water to form the hydronium, so increase our acid, and leave behind the conjugate base. So this is just an equilibrium, right? So the equilibrium constant would look like this. Here's our products, each raised to the coefficient in the balanced chemical equation. So that's what we see here. And then again, here's our reactants, which has our acid and the water raised to the first, since they're both coefficients of 1. But again, we know that pure liquids should not appear in the equilibrium constant expression, and that's because the concentration of water in an aqueous solution is 55.5 molar. The small amounts of acid and conjugate base in the hydronium ion pale in consideration to the concentration of the water. These guys, most might have a concentration of, let's say, 1 molar. Well, that's still insignificant to 55.5 molar. And 1 molar would be a really, really concentrated solution. So basically what it's saying is that the concentration of water is unchanging. It's just a constant, 55.5 molar. So we're simply going to move that over to the equilibrium constant. And that's just going to become part of that constant that we call Ka. So that's our Ka value. So there it is. There's what we would have expected. The equilibrium constant is equal to the concentration of the aqueous products and divided by the aqueous reactants. Again, raised to the power in the balanced chemical equation. Okay, so there it is. There's the acid ionization constant. It's always going to look like this for weak acids. And here's just an example. You don't have to memorize these. You can get these from the tables of chemical data that's posted on Canvas, or if you're using TRO, either first or second edition, it'll have the same values in its appendix. Again, it's a lot easier to just use the tables of chemical data that I posted on Canvas. They're all combined into one, and you're trying to search through the book. So here's just some examples of it. So we can see that we have chloroacetic acid that has a Ka of 1.4 times 10 to the minus 3. And we'll compare that to acetic acid, which has a Ka of 1.8 times 10 to the negative 5. Now remember, the bigger the Ka value, the more products are going to form. Now the products in this case are our acid, the H3O plus or H plus. So the bigger this value, the stronger the acid. So we can see that chloroacetic acid, basically we have, the acetic acid has that CH3, and then the carboxylic acid part of it, the organic part. Well, in chloroacetic acid, all they're doing is replacing some of the hydrogens on the CH3 part with chlorine, which is more electronegative. And so it's basically pulling the electrons that are bonding that acidic proton away from it, making it easier for it to pop off. Now we're going to talk about this, the relative acid-base strengths and how electronegativity and polarity play into that. Okay, we'll get to that at the end of this chapter. But we can see that chloroacetic acid is 2 orders of magnitude. So that's 10 to the 2, that's 100 times. So chloroacetic acid is 100 times more acidic than acetic acid. So it's much, much stronger. It's 100 times stronger acid than acetic acid. Then we can see like carbonic acid is a fairly weak acid, 10 to the negative 7. Certain alcohols, there is a benzene ring here, which I'm not going to get into, but those of you go into organic chemistry will understand that this aromatic ring will actually stabilize this molecule. So in this case, this alcohol can actually lose the H and be slightly acidic, but you'll see that it's 10 to the negative 10, which means it's a really, 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 really weak acid. okay? Way weaker than water itself as being an acid. Carbonic acid, you can see, is almost the same strength as water. Well, water's 10 to the negative 14, so it's again 7 orders of magnitude stronger than water. This is just a little bit stronger than water itself. Okay, it has to be stronger than water to be considered an acid. So again, because of this benzene ring, it's stabilizing the loss of the H plus off the alcohol, but alcohols are normally not acidic. So this is a strange thing. And also, we would not normally write it like this. I just wrote it like this to show that that H is slightly acidic, but we would write this C6H6OH, okay? But again, how do we know that this alcohol is actually acting as an acid? You just look up in the tables of chemical data, and if it has a Ka value, it must be acting as an acid. Okay, next I want to talk about the degree of ionization of a weak electrolyte. So basically, this is just the fraction of the molecules that actually dissociate. So the degree of ionization is just the fraction of molecules that actually dissociate. Now, we could determine the Ka in a number of ways. We could use the electrical conductivity, right? Because these things are dissociating into ions, and the more ions there are, the more conductive the solution is going to be, and we can quantify that. Or we could use some other colligative property as well, right? We know that when things ionize, we could use the freezing point depression or the boiling point elevation. We could use the osmotic pressure. So there's all kinds of different ways we could determine the Ka from the degree of ionization. So these things here are all measuring the degree of ionization, the fraction of particles that actually dissociate. And from that, we can get the Ka, and we'll see that relationship here shortly. Now, with weak acids, we could simply use the pH meter, right? We could measure the pH, and from the pH, we would actually be able to determine the Ka by just using an ice table. And that's generally how we determine Kas and Kbs. We simply measure the pH of the solution. It takes a second. It's non-intrusive, so it doesn't change the solution in any way. So this is just a very easy way to determine Kas, is just to use the pH meter. Okay, let's take an example. So acetic acid, which I'm going to call HACE. Acetic acid is a weak monoprotic acid. Mono meaning it only has one protic, meaning acidic hydrogen. So monoprotic means it only has one acidic hydrogen. Sulfuric acid, H2SO4, is what we would call diprotic. It would have 2 acidic protons. So acetic acid is monoprotic. It only has a single acidic proton. So if we have a 0.014 molar solution of acetic acid, and it has a pH of 3.31 at 25 degrees Celsius, we want to calculate the acid ionization constant, the Ka, right? So the acid ionization constant, or the Ka, for this acid at 25 degrees Celsius. Well, we're going to set up the ice table to do that. Okay, so here's our acetic acid. It's a carboxylic acid. So again, here was that CH3 group I was talking about. And so for chloroacetic acid, it just replaces a couple of these hydrogens with chlorines. And that pulls the electrons from this bonding, right? This is the acid part here. It pulls those electrons away from the hydrogen, which makes this thing pop off easier. Like I said, we'll talk about that in detail at the end of this chapter. So when we throw any carboxylic acid into water, basically what happens is the acidic proton comes off, it dissociates, so it increases the hydrogen ion concentration, and it leaves behind our conjugate base. Now, the reason that carboxylic acids are acidic to begin with is because of a resonance stabilization, right? We could see this thing is going to have resonance because I could have put that double bond here and put the extra set of lone pair here, right? So we have resonance stabilization. So that's why carboxylic acids are acidic. That's why they can lose this H+, because their anion is stabilized through resonance. Okay, back to determining the Ka. So we're going to set up our ice table. We know that the initial concentration was 0.014 molar acetic acid. We're going to ignore the water because it's a pure liquid and it does not appear in the equilibrium constant expression, or in this case, the acid ionization constant expression. We're going to assume that we have pure water. So now remember, from the self-ionization of water, this is going to be 10 to the negative 7. Now, unless you have a very, very weak acid, you can ignore the concentration of the hydronium ion. And I have a homework problem, if you do your homework sets, that shows that certain weak acids, you have to actually take this into account. But I can tell you that on any quiz, any exam, we're going to always assume that this value, this 10 to the negative 7, 1 times 10 to the negative 7 is so small, we could ignore it. So we're just going to say it's 0. We're going to assume it's 0. And we're also going to assume it was pure water. So there was no acetate in solution prior to us dissolving the acid, the 0.014 molar acetic acid in the solution. So that's also going to be 0. And just like we did in chapter 15, we're going to always treat the reaction like it's moving in the forward direction from reactants to products, from left to right. And so we're always going to lose our reactants and gain our products. So we're going to use the coefficients again. In this case, for our acids, they're always going to be 1s. So we're going to lose 1 acetic acid, so minus X. We're going to gain 1 hydronium ion and 1 acetate ion. And at equilibrium, like we always do, we simply add the initial and the change. So this is going to be 0.014 minus X. 0 plus X is X, and 0 plus X is X. Now we know the Ka expression is simply going to be the concentration of the products, each raised to the coefficient in the balanced chemical equation, divided by our reactants, again raised to the coefficient in the balanced chemical equation. We'll ignore any pure liquids or solids, so that's not going to appear. Remember, X is a concentration. Okay, we just kind of ignore the units when we're dealing with equilibrium. But again, X is the molar concentration. It has units of moles per liter. So there's our equilibrium constant expression. So it's going to be X. So remember, Kas are always the equilibrium. And don't forget about those Qs, the reaction quotients. The reaction quotients are always going to be the initial concentrations. But this is K, so it's going to be the concentration X, X for the acetate, and 0.14 minus X for the acetic acid. So X times X is just X squared. Now, we actually know X, right? Because the pH is the hydronium ion concentration at equilibrium. So again, the pH is the hydronium ion concentration at equilibrium. So we just need to, again, take the anti-log of the negative pH, which will give us X. Right? So again, the anti-log of the negative pH, which is just 10 to the negative pH. The pH is 3.31, so 10 to the negative 3.31 is 0.0004897 molar. So that is X. So we'll just plug that into our equilibrium constant expression that we got. And that is going to then give us a value of Ka of 1.77 times 10 to the negative 5. In this case, it's just 2 sig fig, so it's going to be 1.8 times 10 to the negative 5. So there's the Ka. So that's exactly how we measure the Kas of acids. Very easy. We just know our initial concentration, right? Now, most acids are actually solids. Okay, so you would just measure them out on a balance and then add them to a given amount of water, and you calculate the molten molarity from the moles divided by the volume of the solution. Then you just simply measure the pH of that solution. Now, when you do that too, by the way, all of the acid that you add has to dissolve, which it will, okay, unless you're adding an extreme amount where you just basically run out of water molecules to solvate them, okay? But again, we're generally working with dilute solutions. Okay, so once we know the value of Ka, you can calculate the equilibrium concentration of any of the reactants or products at any given molarity. So once we determine this, we never have to determine it again. Now, again, it is temperature dependent, so we're assuming we're always working at about 25 degrees Celsius. Okay, next let's talk about the degree of dissociation. Okay, so I've seen this called degree of dissociation or degree of ionization. Okay, it really doesn't matter. They mean the same thing. We're going to use the Greek letter alpha is its variable. So alpha is the degree of ionization. And all it is the concentration of the conjugate base in the case of an acid. So the conjugate base at equilibrium, okay, divided by the initial concentration of the acid. Again, this is the concentration of the conjugate base at equilibrium, and then this is the initial concentration of the acid. So in our case, we found that since the hydronium ion concentration was 0.000487, well, it's a 1-to-1 ratio, so the acetate was also 0.004897. Our initial concentration was the 0.014, so the degree of ionization was 0.035. Now, if we want the percent ionization, we simply multiply this by 100%. So that basically means that 3.5% of what we added into the solution actually dissociated into the hydronium and acetate anion. The rest remain as intact acetic acid molecules. They are dissolved and they're just floating around in solution, but they're still totally intact. Only 3.5% of those molecules actually dissociated. So it's only that which is going to contribute to the pH, right? The undissociated ones are not increasing the amount of hydronium ion concentration. Now I can show that to you graphically. And so you can see this is the concentration of acetic acid. So let's start at the high concentration. So again, we can see at very high concentrations, the whole way from until you get to about 0.2 molar, less than 1% of the acetic acid molecules actually dissociate. Then once they become more and more dilute, you can see that more and more and more of them are actually dissociating. Now the pH is still going to increase because even though fewer and fewer are dissociating, you still have way more acetic acid molecules in solution. So the pH continues to increase as you increase the concentration. It's just the number of actual dissociated acetic acid molecules, okay, are just a lot smaller. So does everybody see that? So the degree of ionization is actually dependent on the concentration. The higher the concentration, less of the molecules actually dissociate. Okay. Okay, note that in our previous example, the degree of ionization was so small that X was negligible compared to the concentration of acetic acid. So we're going to use this to our advantage. So we're going to say that if the initial concentration divided by the Ka, if that ratio is greater than 100, we're going to be able to ignore the minus X term in our equilibrium constant expression. And what that means, we're not going to have to use the quadratic formula. So you want to apply this every time you're looking at a weak acid equilibrium. Because if you don't have to use a quadratic formula, you don't want to. It's just a waste of time. Okay? So again, since anytime this ratio is greater than 100, we're going to be able to ignore the minus X term. And basically, if we do that, the worst we could possibly have is a 5.5% uncertainty or error in our calculation. And with the acids, we're going to find out that that isn't so bad because the acids will fluctuate quite a bit anyway. Okay? So again, in the case of our acetic acid, we had a concentration of 0.014 and the Ka value was 1.8 times 10 to the negative 5. So that's going to equal 7.78. Now, the stronger our acid becomes, the smaller this number becomes. So this works for weak acids. But again, as the acid becomes stronger and stronger, I believe it's somewhere around 10 to the negative 3, 10 to the negative 4 region, that this breaks down and it doesn't work anymore. But the weaker the acid, the better this actually works. Okay? So since that's greater than 100, we would be able to ignore the minus x term, this term right here, not this, right? We can't ignore all the x's or there's nothing to solve for. But we can ignore this minus x term if this ratio is greater than 100. So we're going to be able to ignore that minus x term. And now all we have to do is bring the 0.014, multiply it by the Ka, take the square root of it, and now we have the hydronium ion concentration. So very simple. But again, if this is actually less than 100, then you're going to have to use the quadratic formula to solve the problem. Okay, so using x gives us a value of 1.76 times 10 to the negative 5. And not using x, just ignoring it, gives us a value of 1.71 times 10 to the negative 5. So you can see that the values are very close, 3.5% error in our calculation. So again, that's why we're going to be able to ignore this minus x term, because the uncertainty is, or error is really small. Okay. And again, like I said, if this simplifying a function, if this number is greater than, as less than 100, then you're going to have to use the quadratic formula. Otherwise, your error will be too big, too high. Okay, so let's try another example. I want to know, what is the pH of a solution at 25 degrees Celsius when 0.231 grams of acetylsalicylic acid, or aspirin, which is a monoprotic acid with this formula, is dissolved in 250 milliliters of water, so or 0.25 liters of water. So first thing we're going to need to do is determine the initial concentration, and to do that, it's going to be moles over liters. So we're going to have to convert this grams to moles by simply dividing by the molar mass of acetylsalicylic acid. And so that'll give us 0.00128 moles of the aspirin. And we're going to divide that now by the volume of the solution, the 0.25 liters. And that gives us initial concentration of aspirin of 0.00510. Okay, so there is our initial concentration. Like I said, most acids are actually solids, and so this is how we would determine our initial concentrations. Okay, now we're going to set up our ice table. So we have our, I'm just representing the acetylsalicylic acid as HACS, so that's our aspirin. And it is reacting with water, transferring a proton to water to form the hydronium and then the conjugate base. Our initial concentration we just determined is 0.0051. We're going to ignore the pure liquid. Again, we're going to assume that the self-ionization of water is so small that it's negligible, so we're going to say it's 0. And again, we're assuming we're starting with clean, pure water, so there would be no conjugate base in the solution, so it too is 0. Next, our change, we're always going to lose our reactant, so minus 1x. We're going to gain our product, so plus 1x for the hydronium and plus 1x for the conjugate base. At equilibrium, we're just adding the initial and change, so this is going to be 0.0051 minus x. 0 plus x is x, 0 plus x is x. So we're going to set up our equilibrium constant expression. So again, our products, each raised to the coefficient in the balanced chemical equation, divided by our reactants, again, raised to the coefficient in the balanced chemical equation. We're going to need to look up the value of Ka. Okay, so we're going to go to our tables of chemical data. We'll look up the value of Ka for aspirin, and that value is 3.3 times 10 to the negative 4. Okay, so we're going to plug that in. And then again, our equilibrium concentrations, the hydronium and the conjugate base are both x. X times x is x squared. and then the concentration of our acid, undissociated acid, at 0.0051 minus X. Now, I want to know, can I ignore this minus X term? So what I'm going to do is I'm going to take the initial concentration, I'm going to divide it by the Ka value. That gives me a value of 15. That is less than 100. I am not going to be able to ignore the minus X term, so I'm going to have to use the quadratic formula. Okay. So I just got to multiply it all out, right? I'll multiply the denominator over to here. And then I'm going to take these terms and subtract them from this side so that we get this, right? We're going to have A, which we can see is 1, plus BX plus C is equal to 0. So that's all I'm going to do is I'm just going to rearrange this into these terms and you will get this. So I can see, again, this would be, I wrote it like this, but when you write it, it's just going to be minus 1.7 times 10 to the negative 6. But remember, it's always plus. So if it's a negative sign, that means that that value is negative. So our A in this case is 1, our B is 3.3 times 10 to the negative 4, and our C value is negative 1.7 times 10 to the negative 6. So now we're going to plug that into the quadratic formula, that X is equal to B plus or minus the square root of B squared minus 4AC, all divided by 2A. And we're going to get two values, right? Because we've got the plus term and the minus term. So we plug them in. We get two values of X of 0.00115 or negative 0.00148. Now, again, as we stressed last week, the value of X can be positive or negative. It doesn't matter. If it's positive, it means that the reaction's traveling in the forward direction. And if it's negative, it means that we've overshot and the reaction is traveling from products back to reactants so that we get that right ratio of reactants and products. That's, of course, our Ka, right? Okay, so now looking at this, I can tell that if I use the negative value, I'm going to get a negative concentration. Now, that's something we can never have. We can never have a negative concentration. So therefore, we can eliminate this X value because it would give us a negative concentration, and we can't have that. So this must be our value of X. So it was asking for the pH. Well, X is our equilibrium concentration of the hydronium ion. So we just need to take the negative log of X. And so our pH then is going to be 2.94. And it should make sense. If I dissolve an acid in water, my pH should be less than 7. If I dissolve a base in water, my pH should be greater than 7. So this is a self-check. You should be looking at your numbers and going, okay, does this actually make sense? Right? In this case, it does. This number is less than 7, and we would have expected it to be less than 7 to be in the acidic solution. Okay? Okay. Okay. Let's try number 34 from chapter 16. It says, what is the hydronium ion concentration of an aqueous solution of 0.17 molar hypoiodous acid? And then what is the pH? So we want the hydronium ion concentration first. So first thing I would note that hypoiodous acid is not one of our 6 strong acids. Okay, and what is the formula for hypoiodous acid? Katrin, what do you think? What is the formula for hypoiodous acid? So if it's hypoiodous, what did it end in? Did the initial anion end in IDE, ITE, or ATE?
Is it ATE?
Nope, it's ITE when it ends in OUS. Okay, so that means this must have been the hypoiodite anion, plus however many H's, of course, to make it neutral, which would be our acid. So what is the formula then for the hypoiodite?
be HI? No.
HI would be
Yeah, that's a
hydroiodic acid, right? HI would be hydroiodic acid. Just like hydrochloric acid is HCl, hydrobromic acid is HBr, hydroiodic acid would be HI. So the hypoiodite is just going to be OI minus. So then to make it an acid, it's going to be HOI. Okay? So that's our hypoiodous acid. So that's our HOI. Now we could do this one of two ways. I could have written the water with this reaction. And then we have our hydrogen transfer from our acid to the water, right? And I could have given this then. And this is normally the way I'm going to write stuff so that you could easily see. And honestly, if you are struggling with this, I suggest that you always write it in this term so that you could see that the hydrogen ion is being transferred. So now we have an acid in conjugate base and an acid in conjugate base. So we have both of our conjugate acid-base pairs when you include the water. But I also want you to be familiar with the way a lot of folks write it. So once you get comfortable with all of this stuff, if you would use it on a regular basis, you're not going to include the water. You're just going to show this thing as a simple dissociation of our, remember, all acids are soluble. That doesn't make it strong. They just dissolve in water. And we could simply show this as a dissociation reaction. Okay. So this will work with any acid. It'll work with hydroxide bases, except that it would be the hydroxide ion, not the hydrogen ion. But for any nitrogen-containing bases, you always have to add the water in, okay? So again, this and this are the same thing. This is what really happens. This is just a shortcut, eliminating the water out of it. So again, I'm normally going to write it like this because I don't want to confuse folks, but I will do this on occasion because you will see this if you ever have to work with acid-base reactions, okay? Okay, and a lot of you will. Any of you going into just about any of the natural sciences are going to have to work with this at some point in time, okay? Okay, so now we established that it is a weak acid. That means we're going to have to look up the Ka value. So again, you're just going to find that in the tables of chemical data. And the Ka value is 2.3 times 10 to the negative 11. So we can see that this is a really weak acid, right? Really small K value. Okay, so now we're going to set up our ice table. Initial concentration was given to us as 0.17 molar. So that's going to be 0.17. Our hydrogen ion, again, we're going to assume is 0. We're going to assume we could ignore the self-ionization of water, so that would be 0. And again, pure water, so there wouldn't have been any of the conjugate base to begin with, so that would be 0. So again, we're always going to treat the reaction going from reactants to products. So we're always going to lose our reactants, gain our products. So this is a coefficient of 1, so we're going to lose 1 of the acid. Coefficient of 1 will gain 1 hydrogen ion, and coefficient of 1 will gain 1 hypoiodite ion. Equilibrium, always the same. We just add the initial and change. So 0.17 minus x, 0 plus x is x, 0 plus x is x. Our Ka expression, again, just going to be the products, each raised to the coefficient in the balanced chemical equation, divided by our reactants. So there it is, our products divided by our reactants, each raised to the 1 since the coefficients are all 1. Now we can plug in our values. The Ka value was 2.3 times 10 to the negative 11. We have x and X for the hypoiodite, right? Again, these are just the equilibrium concentrations. And then for our acid, that was 0.17 minus X. Now, again, I'd prefer not to have to solve the quadratic formula, so I want to see if I can ignore this minus X term. So again, I'm just going to look at that ratio Ca over Ka, which is 0.17 divided by our 2.3 times 10 to the negative 11. I can already see this is going to be over 1 billion, and it's 7.4 billion to be exact. That is definitely greater than 100. Means we can ignore this minus X term. So now that leaves me with 2.3 times 10 to the negative 11 is equal to X squared over 0.17. So again, this allowed us to ignore that X value. So now I say that X squared is equal to the 2.3 times 10 to the negative 11. I'll multiply both sides by the 0.17. Now I'm going to take the square root of both sides to get rid of the X squared. So that's now just X. Plug this into my calculator and I'm going to get a value of 1.977 times 10 to the minus 6. We got 2 sig figs, 2 sig figs. So this will be 2 sig figs. It asks, what is the hydronium ion concentration? Now, hydronium ion really is this, right? But again, we know that the hydrogen ion really only exists as the hydronium ion. So again, we know that the H plus in our formula here is really the hydronium ion. And so the hydronium ion concentration then to the correct sig figs and rounding will be 2.0 times negative the 6, 10 to the negative 6 molar. Any questions with that so far? Okay, so the second part of this, they just wanted the pH. And the pH, of course, is nothing more than the negative log of the hydrogen or hydronium ion concentration, which is the negative log of our unrounded value, 1.977 times 10 to the negative 6th, which is going to give us a value of 5.7039. That is a 0. There is 2 sig figs in our log, so we'll have 2 significant decimal places. So that is 5.70 is the pH. It's less than 7, and that would make sense for an acid. Any questions about any of this good stuff? Okay, let's try another. Okay, so in order to determine the concentration of an aqueous lactic acid solution, a laboratory technician measured the pH of the solution to be 1.98. What is the concentration of lactic acid in the solution? So basically what it's asking for here is, what is the initial concentration of lactic acid? Okay, so you got to be able to recognize what they're asking for. So they are asking for, what is the initial concentration of lactic acid? So again, we have lactic acid, and this time I will write it with the water. All acids are soluble. So I'm going to write it with the water. It's a weak acid, so double arrow. We know it's going to have a K value. A proton is going to be transferred from the acid to the base, which is water in this case. So that's going to give us the H3O plus, or hydronium or hydrogen ion, and leave behind the conjugate base. So C3H5O3 minus, aqueous. We're going to have to use an ice table for this. And so we're going to need to know the Ka value, which we will simply look up in the book. And the Ka value is going to be, what is it? 1.4 times 10 to the negative 4. Now let's set up our ice table. So if you're dealing with a weak acid and you don't know where to start, or a weak base, start with an ice table. You might not need it, but in most cases you will need it, okay? So I can go through here and I can go, okay, well, they did not give me the initial concentration. In fact, that's what we're looking for, right? This is what we're looking for, is the initial concentration. So I'll come back to that in a second. We are assuming that we had pure water, so we would be able to ignore there'd be no hydronium ion or the conjugate base to begin with, so we know they would both be zeros. Our change, we're always going to lose our reactants and gain our products. All the coefficients are 1, so it'd be minus 1x plus 1x. Okay, but now coming back to this, that's what we're looking for. So that's going to be a variable. We're going to call that y. So y is what we're looking for, the initial concentration of the lactic acid. So now at equilibrium, I know this is just the initial minus, and we're just going to add up these two. So that's y minus x. 0 plus x is x. 0 plus x is x. I know that the equilibrium constant expression, Ka, since it's an acid. Now, you're going to have to know, do I use Ka or do I use Kb? If it's H3O plus is a product, you're using Ka. This is going to become important, especially when you start dealing with the salts. You're going to be asking yourself, well, do I use Ka or Kb? It's very simple. Don't make it hard. If the product is H3O plus, you use Ka. If the product is OH minus, you use Kb. Always. Okay? So you're just looking to see what the product is, and that's going to determine whether you use Ka or Kb. So it's going to be our product. So it is the H3O plus times the concentration of the conjugate base, in this case the lactate ion, divided by the concentration of the reactants. And these are, again, all raised to the first, since all the coefficients are 1. And again, we're going to ignore the pure liquid. Okay, so now we can actually plug, right? So we know the Ka is 1.4 times 10 to the negative 4. That's going to be equal to, we have x and then x, so this is x squared. Then we're going to divide that by the concentration of our undissociated acid at equilibrium, which is going to be y minus x. Okay, I have an issue here because I have two unknowns. So how am I going to proceed with this? Leah, what am I going to do? You got to unmute yourself, hit space.
Would you use the pH value to solve for the H3O plus, and then that's your X? So
yeah, exactly,
right?
So this pH represents the equilibrium concentration of the hydrogen ion or hydronium ion. That's X. So I'm going to use that pH, and again, we know the pH is equal to the negative log of the hydronium or hydrogen ion concentration. So the hydronium ion concentration is going to be equal, I'll bring the negative over, take the anti-log, so that's 10 to the negative pH, 10 to the negative 1.98. They gave us that value in the problem, the pH of the solution. And when they tell you that the pH of the solution is something, you automatically have to assume that it's at equilibrium, okay? Plug that into your calculator, and that is going to give you a value of 0.01047. So this is 2 decimal places, so this will be 2 sig figs. Okay, so there is that. But again, we know this is the equilibrium concentration of H3O. So this is equal to X. So we actually do know X, and we're just solving for Y then. So I'll just rearrange this real quick, right? We're going to bring, well, I'll just plug in the value. So we got 1.4 times 10 to the negative 4 is equal to our X value, which is 0.01047 squared over Y minus 0.01047. We would bring this up. Crap. Okay. And then we'll divide both sides by that. So this would be 0.01047 squared divided by 1.4 times 10 to the negative 4. And then we'll add this value to both sides. So Y then is equal to 0.01047 squared divided by 1.4 times 10 to the negative 4, and then plus 0.01047. And therefore, Y is equal to 0.7934, and it'll be the 2 sig figs. So the initial concentration, HC3H5O3, and again not, indicating that it is the initial concentration, is equal to 0.79 molar.